Yeah, am I audible? Who is in the line? GSN
Yes, sir.
Murthy.
Yes, sir. You are audible,
Yes,
sir.
sir. Yes, sir.
Yeah, good afternoon.
Good afternoon, sir.
Yeah, Jay Shri.
Yes, sir.
No one is attended to the online classes. Sorry, offline classes.
I'm attending, sir.
Yes, Jay Shri.
నేను అటెండ్ అయ్యాను కదా సార్ ఆఫ్లైన్ క్లాస్ కి
ఎన్ని క్లాసెస్ ఇచ్చారండి?
ఓ క్లాస్ కి వచ్చాను సార్.
మరి
నేను ఒక రోజు వచ్చాను సార్, ఇంటి సిరిసిల్ల నుంచి వచ్చాను. ఆ రోజు ఎవరు సార్ వాళ్ళు రాకపోతే మళ్ళీ వెనక్కి వెళ్ళిపోయాను, నేను శ్యామన్న.
ఆహా.
సార్ నిన్న కూడా జరిగిందా సార్ ఆఫ్లైన్ సాటర్డే?
లాస్ట్ క్లాస్ జరిగింది.
నేను అదే ఇప్పుడు నేను ఈ రోజు ఉందనుకుని వద్దాం అనుకున్నాను సార్. నిన్న జరిగిందనే తెలిసింది నాకు.
ఓకే, ఒక్క 2 నిమిషాలు వెయిట్ చేయండి, ఇంకెవరైనా జాయిన్ అయితే చూద్దాము.
సార్ సార్ నిన్నటి క్లాస్ ఏమన్నా ఒక 5 minutes చెప్పగలుగుతారా?
నిన్నటి క్లాస్
ఒక 5 minutes అంటే
తీసుకోలేదు.
ఆహాహా.
తీసుకున్న వాళ్ళు మోహన్ సారు, మురళి సారు,
ఓకే.
వాళ్ళు జాయిన్ అయినప్పుడు వాళ్ళని అడగండి.
ఓకే
Brief
ఓకే
చేస్తాను. ఓకే,
జస్ట్ టాపిక్స్ గురించి అంతే. ఏం టాపిక్స్ అని?
నేను ఒక 2 నిమిషాల్లో జాయిన్ అవుతారు. ఈ లోపు ఎవరైనా జాయిన్ అవుతారని చూడండి. ఓకే,
సరే సార్.
Yes, am I audible?
Yes, sir.
Am I audible to you?
Yes, sir. వినపడుతుంది సార్.
Sir, you are audible, sir.
Yeah. I'm going to start this session. Yeah. All of you from STML, 208 Study Center, is there anyone from Tirupati, Vizag? Please raise hands. Is there anyone? Okay, thank you. Today I'm going to start with the organic photochemistry. Those who are not attended to the first two blocks, if we have time, we'll discuss personally later, right? First week in this online sessions, we are going to complete the fifth last two blocks. Those are block 3 organic photochemistry, and block 4 is stereochemistry 2 actually. This is extension to the first year stereochemistry. Okay, now today I'm going to start the organic photochemistry. In that, the first unit is electronic transitions. The first unit 2. In this unit 1, or as per the books, it is unit 11, electronic transition states. Right. Before going to the unit, just I want to give the brief. What is organic photochemistry? How it is differentiated from the conventional synthetic process, that is the heating methods. How it is different. Suppose if you take a reaction vessel, you take some reaction contents, right, reactants. We can do the reaction by just heat it using the flame. From the flame, heat will be transferred to the reactants. All gets excited. Reactants are all gets excited. Then reaction will proceed. In this process, during entire reaction, the reactant, whatever the product produced in that, whatever the reactive intermediate produced in the reactions are in the same energy state. In the heating reactions, all the contents are present in the reaction mixture are existing in the same excitation level or same heating conditions or same conditions. Okay, right. Whenever the same reaction, suppose the alternate is possible, the same reaction is carried out whenever we are passing a beam of ray, that ray is transmits through the reaction mixture. This, you know that any light is the mixture of different wavelengths of lights. That is a ordinary light, white light, or if you take a this ordinary light is the combination of 7 colors of lights or 7 different wavelengths, right? Along with the some ultraviolet radiation and along with the some infrared radiations, right? And that means different wavelengths of lights are mixed in the white light. This white light is passing through the reaction mixture. Then the reactants gets absorbed some light energy, then gets excited. This notes is visible to you all? నాగరాజు,
Yes, sir.
కనిపిస్తుందా? నేను రాసేది
కనపడుతుంది సార్.
మూమెంట్ కనిపిస్తుంది కదా? ఓకే,
కనపడుతుంది సార్. కర్సర్ కూడా మూమెంట్ కనపడుతుంది సార్.
yes. A white light is passing through the reaction mixture. Now, whenever we are passing this light through the reaction mixture, the whatever the contents present in the reaction vessel absorbed some light energy. Not get all the reactants will not absorb. Suppose two reactants are there, A and B. Whenever you are passing the light, the A or B will be absorb the radiation, light radiation, then gets excited. That means higher excitation level will reach. This excited molecule bombarded with the next molecule, then proceeds the reaction. It will give the reaction, or it will give the product. Now this reaction is known as photochemical reaction. Photochemical reaction. In the most of the photochemical reactions are highly specific reaction. For example, photosynthesis. The photosynthesis what? Chlorophyll is excited. Chlorophyll is excited. Then whatever the carbon dioxide absorbed by the plant and water will be reacted. That means that chlorophyll is binds with the water and carbon dioxide that synthesizes the remaining process of the carbohydrates. Similarly, in general, organic molecules are also reacted in presence of light. In presence of light, it is what is the reason? The light is existing with multiple wavelengths of radiations, electromagnetic radiations. These electromagnetic radiations are absorbed by the reactants, then gets excited. These excited molecules are reacting with the other reactants which are present in the ground state that leads to the formation of products. Now these reactions are known as organic photochemical reaction. The chemistry associated with this photochemical reaction are named as organic photochemistry. Right. When we compare the thermal reactions and photochemical reaction, just simple comparison between the photochemical reactions comparison between thermal reactions and photochemical reactions. Now take a one-sided thermal reactions and one-sided photochemical reactions. In these thermal reactions, all the reactant molecules gets absorbed, molecules present in the system absorbed heat energy and gets the same amount of same amount of heat energy. Same amount of heat energy. Right. When you come into the photochemical reactions, an individual any number of reactions are there, but individual molecule gets absorbed radiation, and converted into excitation state. It means excited to excitation state or activation state, activated state. We can call it. Both are same. Excited state, then undergoes reaction with ground state molecules. By simple energy transfer and produces product. Simple. Suppose, as I explained previously, if you treat like this here, whenever we are heating the contents, all the molecules gets absorb the heat energy, and they are existing in the same state. Then they are undergoing the reaction, they lead to the formation of product. But in the case of photochemical reaction, we are passing through the light. When we are passing this light, the molecule present in the reactants, in the reaction mixture, individual molecule can absorb the light energy and get excited. That excited molecule reacted with the ground state molecules, then leads to the formation of product. These reactions are highly specific reactions. These reactions are, whenever we are coming to photochemical reactions, these reactions are highly stereospecific reactions. When we coming to the thermal reaction, we cannot predict this stereospecificity. We cannot predict the stereospecificity until products obtained, products recovered. Right. In these photochemical reactions, carried out in two regions: visible light region, that is almost 400 to 800 nanometer region. The energy associated with this light range is 38 to 72 kilocalories. 72 kilocalories per mole of energy. Wherever if you are using, instead of visible light, if you are using ultraviolet, it is in the range of the radiation is 200 nanometers to 400 nanometers. The energy associated with this region is 72 kilocalories to 143 kilocalories. 143 kilocalories per mole, right? Now, these reactions, when you're coming to the photochemical conditions and photochemical reactions and thermal reactions, here both are associated with the excitations, electron transfers. But in the case of thermal reaction, this electron transfer takes place in the one electron in between the vibrational and rotational level only. But when we come into a photochemical reaction, the electronic transactions, electron transitions that takes place between the molecular energy levels, molecular or electronic energy levels. Okay, these electronic energy levels from the transfer of electron from the ground state to the higher level of excitation levels are known as electronic excitations or electronic transition. Electron transitions means the electron is excited from the ground state to higher excited level, then it undergoes the decaying. Then later it is slowly to decay to the ground state. Now this process is known as electronic transition. This process is known as electronic transition. That means absorption of radiation by molecule causes electronic transition, electronic excitation, or this electronic excitation leads to the decaying of that excited level to the lower level. Then this is known as electronic transition. Electronic transition. In this electronic transition, electron is promoted from the bonding molecular orbital to the higher energy orbital. That is the vacant anti-bonding molecular orbital. Bonding orbital to the anti-bonding orbital. If you are attended to the pericyclic reaction, we can easily understand the what is the bonding molecular orbital and what is the anti-bonding molecular orbital. But I will give the brief review of that bonding molecular orbital and anti-bonding molecular orbital here. Please look at here. Suppose if you take the sigma bond, the sigma bond is generated in organic molecules is CC bond, CC single bond. Okay, this CC single bond, suppose here it is the sp3 hybridized, it is also sp3 hybridized. Two sp3 hybridized orbitals are linearly overlapped to produce a strong bond, that is sigma bond, right? This sigma bond is undergoing the LCAO, that is linear combination of atomic orbital. That means sp3 hybrid orbital of one carbon and sp3 hybrid orbital of another carbon, carbon 1 and carbon 2, both are undergoing the LCAO. That leads to the formation of molecule. These are treated as atomic orbitals. These atomic orbitals are undergoing the LCAO that produces the two bonding orbital, molecular orbital. One is the sigma bonding molecular orbital, and another one is sigma star. This is anti-bonding molecular orbital. This and this sigma bond is associated with the two bond pair of electrons. This bond pair of electrons are filled in when you come into the energy levels. This is the whatever the line. This is dotted line is known as non-bonding molecular orbital energy level. Non-bonding molecular orbital energy level. Similarly, if you take the energy level diagram, this is the sigma bonding molecular orbital. Sigma bonding molecular orbital. This is the sigma star anti-bonding molecular orbital. Now, the two electrons, these electrons are filled in the molecular orbital based on the by following the Aufbau principle, Hund's principle, and the Pauli's exclusion principle. Based on that, lower energy orbital get filled by the electrons first. Therefore, the two electrons are filled into this sigma orbital, sigma bonding molecular orbital. Now, when we are providing the energy, this is the ground state electronic configuration of sigma bond, that is sigma 2, sigma star 0. Here, the sigma bonding molecular orbital is filled. Therefore, this is known as HOMO. HOMO means highest occupied molecular orbital. Here, the next orbital, this is the anti-bonding molecular orbital, that is the sigma star. It is the empty orbital. Therefore, it is readily accepting electron whenever we are giving the energy. Now, this molecular orbital is known as LUMO, lowest unoccupied molecular orbital. Now, if you are providing energy in the form of thermal or photochemical, the electron is excited from the sigma to sigma star, right? This is a non-bonding molecular orbital energy level. After excitation of one electron from the bonding molecular orbital to the anti-bonding molecular orbital. The electronic configuration here sigma bonding molecular orbital. This is a sigma star anti-bonding molecular orbital. The electron in the sigma bonding molecular orbital is having one electron. Sigma star anti-bonding molecular orbital is having one electron. This is known as first excited state electronic configuration of sigma bond in a molecule. Now, this is electronic configuration is sigma 1, sigma star 1. Now, here sigma star is the highest occupied molecular orbital, but in this case there is no LUMO, there is no empty orbital. Therefore, it is HOMO is the sigma star anti-bonding molecular orbital, and there is no LUMO. Now, if you take the phi bond also, CC phi bond, the sigma bond is already we discussed here, but here whenever we are considering the phi bond, C double bond C, the phi bond will be considered. That means the C phi bond will be generated by the sidewise overlapping of unhybridized p orbitals of each carbon. Unhybridized p orbital. This is the unhybridized p orbital. These unhybridized p orbitals undergoing the overlapping, sidewise overlapping, that leads to the formation of phi bond. Now, these p orbitals of this carbon, both unhybridized p orbitals of carbon atoms undergoing LCAO, that means linear combination of atomic orbital, LCAO, that leads to the formation of two molecular orbitals. One is phi molecular orbital. The phi molecular orbital is like this. Phi molecular orbital is like this. And another one is Phi star molecular orbital. Phi star molecular orbital. This is known as lowest. This is the lowest energy molecular orbital. That is the reason this is known as bonding molecular orbital. It is the highest energy molecular orbital. This is known as anti-bonding molecular orbital. In the bonding molecular orbital, the number of nodes are 0. Therefore, the phase allocation is like this. And in the case of Phi star molecular orbital, there is a node point is there, where the electron finding the probability of finding of electron is 0. That is called as node. Now it is having node, right? Now, when you coming to the electronic energy profile diagram, this is the non-bonding energy level, and this is the Phi molecular orbital, and this is the Phi star molecular orbital. And in the Phi bond, also having two electrons. Phi electrons are two electrons. The two electrons are filled in the ground state energy level into the Phi molecular orbital, bonding molecular orbital. Now, this is known as ground state electronic configuration of Phi bond or ethylene, right? Now, this is the Phi molecular orbital is known as HOMO, highest occupied molecular orbital. Phi star is the LUMO, lowest unoccupied molecular orbital. Right? Whenever we are providing some energy in the form of thermal or photochemical, the electron is excited from the Phi to Phi star molecular orbital. Right? Now, the molecular orbitals are sigma is having one electron, bonding molecular orbital, and sigma star is having one electron. This is the anti-bonding molecular orbital. Now, this is this is known as first excited state electronic configuration of Phi bond, and here the ground state electronic configuration is Phi 2 and Phi star 0. Here the first excited state electronic configuration Phi 1, Phi star 1. Right? Here the sigma is coming. Okay. Phi star. This Phi star is the HOMO, highest occupied molecular orbital, and there is no LUMO in this case. In the excited state level, there is no LUMO. Right? These are the electronic excitations. These excitations are very much important in the photochemical reactions. What these excitations are transitions. Generally, we see in the transitions sigma molecular orbital to sigma star molecular orbital. That is, the electron is excited from the sigma to sigma star. This is called sigma sigma star transition, electronic transition. This is known as sigma sigma star transition. Now, when you take the phi molecular orbital, phi to phi star, that is, electron is excited from the phi molecular orbital to the phi star molecular orbital. This is known as phi to phi star transition. Phi to phi star transition. Right. Generally, these sigma sigma star molecular orbital electronic transitions are generally seen in the saturated compounds, in the alkanes like compounds. But this is the higher energy transition. This is the higher energy transition. This is the, when you compare to the sigma sigma star transition, phi to phi star is lower energy transition. Phi to phi star. Okay, sigma you can take the phi. When you compare the energies, delta, you can take the delta E. Yes, delta E sigma is greater than the delta E phi. Okay, this is generally seen in the CC double bond compounds. CC double bond unsaturated compounds, or CC double bond C compounds are also.
Sir, sorry to
But when
interrupt
you're coming
you.
to the carbonyl compounds,
Hello, sir.
yeah, tell me.
సారీ టు ఇంటరప్ట్ యూ సార్. యాక్చువల్లీ మనకు సిగ్మా బాండ్ పై బాండ్ లో మనకు ఫోటోకెమిస్ట్రీ రియాక్షన్ జరిగినప్పుడు పైకి ఒక ఎలక్ట్రాన్ ఎగ్జైట్ అయింది కదా సార్. అయినప్పుడు పై దాన్నేమో హోమో అంటున్నాం, అది లోయెస్ట్ అన్ఆక్యుపైడ్ మాలిక్యులర్ ఆర్బిటాల్ లేదు కాబట్టి తీసేసినాం. కానీ రెండిట్లలో ఒక్కొక్క ఎలక్ట్రాన్ ఉన్నప్పుడు రెండు హోమో ఎందుకు కాకూడదు సార్?
రెండు కావు. ఇక్కడ ఏం చెప్తున్నాం? When the label is itself indicating that homo means highest. Highest means highest energy.
Okay, sir.
Highest energy. O means occupied. Occupied molecular orbital. Okay. This indicates that whatever both are having the same one electron, but which
Yes,
one
sir.
is having the highest energy?
The upper one.
Phi and phi or phi star?
Phi star is having higher energy.
Higher energy. Therefore, that becomes a highest energy occupied molecular orbital. But there is no vacant here. Vacant orbital is not there. Due to that reason, we cannot say the no LUMO.
LUMO
Here,
is not there.
no LUMO.
But sir, without photochemical reaction, also we have homo LUMO. Na?
Actually, without photochemical reaction, we cannot say that.
But you have
in
written,
absence
sir.
of photochemical conditions,
Okay, sir.
molecule is always treated as existing in the ground state. Ground state means this one. Ground state means this one. That means
Yes,
any time the molecule is existing in the ground state. That is a general belief.
Okay, sir.
Molecule is in the stable form. It is not involved in any kind of reactions. Then that is existing in the ground state.
Okay, sir.
Whenever we are applying external energy like a thermal energy or photochemical energy,
Yes, sir.
that energy is absorbed by the molecule, then it gets excited. Then it reaches to the first excited state or upper excited state.
Yes, sir. But ground state electronic configuration, ఇప్పుడు పై దగ్గర తీసుకోండి, పై బిఎంఓ రాసిరు కదా, పై స్టార్ ఏబిఎంఓ ఉంటది కదా సార్.
ABMO, this is
ఉంటుంది.
ABMO.
సో పై బిఎంఓ పైన హోమో రాశారు. సో ఇక్కడ పై హైయెస్ట్ ఎనర్జీ పై దానికి ఉన్నప్పుడు కింది దానికి హోమో ఎట్లా అవుతుంది సార్?
ఇక్కడ ఏమన్నాం? 5 BMO, that is 5 bonding molecular orbital.
Yes, sir.
Is the homo.
Yes, sir.
Homo means ఏంటి ఇక్కడ? What is the highest occupied molecular orbital?
ఇక్కడ ఎనర్జీ అనకూడదా సార్?
In both the you compare that phi and phi star, which one is occupied?
Yes, sir.
Phi is occupied.
Phi is occupied.
Phi is occupied, na? When
Yes,
phi
sir.
is occupied, which one is having highest energy? Phi star is Phi star is the highest energy. No
Yes,
doubt
sir.
about that. But
Yes,
it
sir.
is vacant.
Okay,
But
sir.
we need to consider which one is occupied one.
Yes,
It's a
sir.
higher energy.
Okay,
This is
sir.
occupied, in which it is the occupied orbital. All over the occupied orbitals, phi is the highest energy and occupied. then it becomes the HOMO, highest occupied molecular orbital. Now coming to the LUMO,
Yes,
lowest unoccupied, that is the vacant, that should be vacant orbital.
Yes, sir.
And second condition is lowest energy. First condition is it should be unoccupied, that is vacant orbital. And second condition is should have the lowest energy.
ABM ఒక highest energy ఉంటుందని చెప్పారు కదా సార్.
Here only two orbitals are there. We cannot easily understand that this is the HOMO, this is the LUMO.
Yes, sir.
Right? Whenever multiple number of orbitals are there in the pericyclic reactions, we discussed about the molecular orbitals of 1,3 butadiene. Right? This is the 1,3 butadiene. Two double bonds are there. Phi system. This is the conjugated Phi system. How many carbons are there? 1, 2, 3, and 4. Each carbon is having unhybridized p orbital. Due to the presence of this unhybridized p orbital, it is undergoing the it is overlapping with the another unhybridized p orbital of the carbon. That leads to the formation of this pi bond. Right? Therefore, all 4 carbons are having 4 unhybridized p orbitals. These 4 unhybridized p orbitals are undergoing linear combination of atomic orbitals that leads to the formation of 4 molecular orbitals. 4 molecular orbitals. That one in that here we need to represent like this. This is the first one molecular orbital psi1, psi2, psi3, and psi4. These are the molecular orbitals. Lower energy molecular orbitals, these are bonding molecular orbitals. These two are anti-bonding molecular orbitals. Right? What is the psi1? Psi1 is this one. Okay, with psi1 is having 0 nodes. It is the n. If you treat n minus 1 number of nodes are there. You read the pericyclic reaction, you can understand. This is the psi2. It is having 1 node. Right? Psi3. Two nodes. No, one node is here, one node is here. How these node points are assigned are discussed in the pericyclic reactions. You read that. And psi4. Each bond is having one node. 1, 2, 3. 3 number of nodes. Right? How many electrons are there? Totally 4 electrons. Then, what is the ground state electronic configuration when we coming to this? 2 orbitals are the bonding molecular orbitals, and that is psi1, psi2. 2 anti-bonding molecular orbitals, psi3 and psi4. Right? Now, how many electrons are there? 4 electrons. The 4 electrons filled in the lower energy orbitals. These are the psi1. 2 electrons are filled in that psi1, and the remaining 2 electrons filled in psi2. Psi3, psi4 are empty. This is the ground state electronic configuration of 1,3 butadiene. Right? In that, what is the HOMO? What is the LUMO? You can say that here.
Above one is LUMO. Other, yes, sir. Psi1, psi2 is a HOMO, sir.
Both are not HOMOs. Only one HOMO, one LUMO is existing for a molecule.
Yes, sir. psi1, psi2 రెండిట్లో ఎలక్ట్రాన్స్ ఉన్నాయి కదా సార్. సో psi3, psi4 లో ఎలక్ట్రాన్స్ లేవు కదా సార్. సో నేను ఏమనుకుంటున్నా అంటే psi3, psi4 LUMO అనుకుంటున్నా, psi1, psi2 HOMO అనుకుంటున్నా సార్.
No.
Okay, sir.
You did not understand the condition.
Okay,
HOMO
sir.
means highest energy molecular orbital with occupied. LUMO means lowest energy molecular orbital with vacant or unoccupied. Now tell me, psi1, psi2. Which one is the highest energy?
Psi1 ఉంటది కదా సార్. Psi2
psi1 and
సార్.
psi2.
Psi2
Which one is the
ఉంటుంది
highest
సార్.
energy? When you coming to this is the energy indication. This is
Yes sir.
arrow.
Yes sir. Yes
From
sir. Psi2
moving from
ఉంటుంది
down
సార్.
to up, energy is increasing.
Yes sir. Above principle
Yeah.
ప్రకారం yes sir. Psi2 is the highest
psi2
energy
is
sir.
the highest energy.
Yes sir.
And whether it is filled or not, occupied or
It
not.
is filled sir. It is filled sir.
Occupied. That's why
Yes,
this becomes HOMO.
Yes sir. Understood sir.
Psi2 is HOMO.
Yes sir.
Now coming to the LUMO.
Yes sir.
Lowest energy. Which one is lowest in the psi2, psi3 and
Psi3,
psi4? Both are
psi3.
vacant orbitals.
Psi3.
Which one is vacant?
Psi3 both are vacant, but Psi3 is the lowest
Lowest
unoccupied.
energy orbital.
Yes sir.
Lowest energy molecular orbital.
Yes
And
sir.
condition is unoccupied. Therefore,
Yes,
psi3
sir.
is the LUMO. Now you can understand. Right? In similar way, you can understand the sigma star orbitals and phi star orbitals. Okay, these are known as electronic excitations. For this is the ground state electronic configuration of 1,3 butadiene, that is psi12, psi22, psi30, psi40. Then whenever we are providing the energy, the electron is excited from the psi2 to psi3.
Yes sir.
Then the 2 electrons present in psi1, 1 electron is present in the psi2, 1 electron is present in psi3, vacant it is psi4. Now tell me, what is the HOMO, what is the LUMO? Highest occupied molecular orbital, highest energy molecular orbital with occupied. Don't recognize whether it is the bonding or anti-bonding. You neglect it. First,
Okay,
those are
sir.
the orbitals or not?
Sir,
Those
sir, two orbitals, 2 electrons ఉన్న దాంట్లో psi1 ఒకటంటే full గా ఉంది సార్.
No. Here the occupied means not fully occupied, not.
Okay, sir. So it will be psi3 sir.
Occupied.
Psi3
Whether
sir.
it is the electron is present or not. That's it.
Psi3 sir. HOMO psi3 అవుతుంది sir. Yes sir.
Psi3 is having the highest energy. Therefore, it
Yes,
is
sir.
the HOMO.
Yes sir.
Now, which one is the vacant and with lowest energy?
Psi4 sir.
Yes. Fully vacant. Vacant means fully vacant here.
Yes sir.
LUMO. This is the LUMO.
Yes sir.
Right. This is the way you need to alert the HOMO and LUMO.
Okay sir.
Okay. Now, when you coming to the carbonyl compounds, this is the phi and phi star and sigma star electronic transitions. These transitions are generally sigma star transitions and phi to phi star transitions. And the next type of transitions are, if you're coming to the carbonyl compounds, these are the very general things to understand this kind of transitions. Carbonyl compounds are having C double bond O group, right? Here the pi electrons are there, on which oxygen, 2 lone pair of electrons are there. 2 lone pair of electrons are there, right? Here this carbon is sp2. This carbon is sp2. Here this oxygen is sp hybridized orbital, right? Now when you coming to this oxygen, 2 sp2 hybrid orbitals are there. Sorry, 2 sp hybrid orbitals are there. 1 sp hybrid orbitals form the sigma bond with the carbon. Form the sigma bond with the carbon. Look at here. Suppose this is the carbon. It is sp2 hybrid orbital, and this is sp hybrid orbital. It generates the 1 sigma bond, right? Next, carbon is having 1 unhybridized p orbital. This is unhybridized p orbital, and total 3 sp2 hybrid orbitals. 1 sp2 hybrid orbital and another sp2 hybrid orbitals. These sp2 hybrid orbital, suppose these are hydrogens, it is binding like this, right? Now here this oxygen, two sp2 hybrid, sp hybrid orbitals are there. This is one sp hybrid orbital is involving the sigma bond with the carbon. Next, this is the another sp hybrid orbital. We cannot it is the linear manner, right? This is one sp hybrid orbital, this is another sp hybrid orbital. This, along with this oxygen, it is having two unhybridized p orbitals. This is one unhybridized p orbital and another unhybridized p orbital is like this. These two unhybridized p orbitals undergoing overlapping, that leads to the formation of one pi bond between the carbon and oxygen. Next, here two vacant orbitals are there. One sp hybrid orbital and one p unhybridized p orbitals are vacant. In that, one sp hybrid orbital is having one pair of electron, and this is also having one pair of electrons. This is also having one pair of electron. This pair of electron is highly stable. It will not interact with any reactions. But whatever the lone pair of electron present in the unhybridized p orbital is easily polarized. Oxygen can easily donate this pair of electrons during the nucleophilic attacking reactions. Right? Now, these electrons are named as N electrons or non-bonded electrons. These non-bonded electrons are also undergoing the transitions. The energy, whenever we are coming to the showing the energy states, this is the non-bonding energy level, right? This is the sigma, this is the phi. Non-bonding electrons are here, N electrons, and Phi star orbital and sigma star orbital, right? Now, here the two electrons are there, here the two electrons are there, here the two electrons are there. Whenever you are providing energy, the electron is excited, easily excited from the N orbital to the Phi star orbital. N orbital to the Phi star orbital. Then, this transition is called as N2 Phi star transition. This transition is known as N2 Phi star transition. Sometimes, if it is the higher energy transitions, upper excited transition, the electron may excited from the N2 sigma star also, right? Or the electron is excited from the Phi to Phi star, or sigma to Phi star, or sigma to sigma star. These are the general type of electronic transitions, that is sigma, sigma star, Phi, Phi star, N, Phi star. Next, N2 Phi star, sigma to Phi star, very rare conditions Phi to sigma star. You can hear
N2 sigma
these
star
are
ఉండదా
the
సార్?
yes,
N2 sigma star ఉండదా సార్?
yeah, possibilities. We cannot say directly. It is the hypothetical assumptions only, right? The electron is excited from the sigma to sigma star, suppose, or the electron is excited from the Phi to Phi star. The electron is excited from the N to Phi star. These are the general transitions. Higher energy transitions. Okay, sigma to Phi star. Phi to Phi star is already known, and Phi to sigma star. These are the actually symmetrically forbidden transitions. This is symmetrically allowed transition. One by one transition I will tell you. The sigma to sigma star transition, it is symmetrically allowed. Symmetrically allowed transition, but energetically forbidden. Energetically forbidden. Similarly, when you come into the Phi to Phi star, symmetrically allowed, and energetically allowed. Energetically allowed. N2 Phi star, symmetrically forbidden. Symmetrically forbidden, but energetically allowed. These are the both energetically forbidden and symmetrically forbidden. In both the cases, forbidden. Generally, these kind of transitions are not occurred, not seen. Okay. Generally seen transitions are Phi to Phi star, sorry, sigma sigma star, Phi to Phi star, N to Phi star. Even though here sigma sigma star is also neglected because it is high energy transition, high energy electronic transition. Even though symmetrically allowed, it will not occur in the, most of the cases, right? Now, in the entire organic photochemistry, we've seen that Phi to Phi star transitions and N to Phi star transitions. Look at here, Phi to Phi star transitions are symmetrically allowed and energetically allowed. When you comparing the Phi to Phi star transition and N to Phi star transition, comparatively energy, right? This is the Phi to Phi star energy level, right? This is the N energy, N electron, sorry, N orbital position. This is the N orbital. Look at here, the energy gap between the N to Phi star. Suppose this is the E1, and the energy gap between the Phi to Phi star, E2. The delta E2 is greater than delta E1. That's why energetically allowed, N to Phi star is energetically allowed. But when we compare into symmetrically Phi to Phi star is allowed, right? But in the case of N to Phi star transition, the N orbitals and Phi molecular orbitals are arranged perpendicular manner. Look at here. N2 Phi star. These two are the p orbital, unhybridized p orbitals. Right? This oxygen, it is having two unhybridized p orbitals in such a way that perpendicular to each other, not the parallel manner. Therefore, these two orbitals are oriented in the two different phases or two different planes. Therefore, these two orbitals are geometrically not nearer to each other. The electronic transition is not possible in such case. But the transition of electron requires lower energy from the non-bonded electron orbital to the Phi star orbital. The Phi star orbital is coming from the unhybridized p orbital. Here also, non-bonded electron is also present in the unhybridized p orbital. This is treated as non-bonding orbital. This is considered as the Phi star orbital. This Phi star orbital and non-bonding orbitals are perpendicular to each other. Now, whenever we are assigning the symmetric symbols, this is the non-bonding orbital is getting the unzeroed symbol. This is getting the zeroed symbol. From transition of electron from the G-rate to G-rate or G-rate to G-rate is forbidden symmetrically. But these two are nearer to each other, even though they are perpendicular to each other. The energy gap between them is very lower. Due to that reason, the electron is excited from the n orbital to the Phi star molecular orbital. That is the reason N2 Phi star is more probable when 9 non-bonded electrons are generated. Just a minute. Right. I think you understand why these pi to Phi star transitions and N to Phi star transitions are generally seen in the photochemistry. Right. Now, these transitions are N to Phi star transitions and Phi to Phi star transitions leaves the several types of excited states. The N to Phi star or Phi to Phi star transitions leads to the several kinds of excited states. Those are called as singlet excited and triplet excited states. These can be explained based on the Jablonski diagram. I think Jablonski diagram already discussed in the photochemistry of physical chemistry. In first year physical chemistry, Keshav sir already explained the Jablonski diagram. Are you remembered?
Yes, sir.
Yes.
మర్చిపోయాను సార్, చదివినా కానీ మర్చిపోయాను సార్.
చెప్పారు కానీ మర్చిపోయారు.
ఎస్ సార్.
సరే, ఓకే. First you need to understand what is the singlet state, what is the triplet state. Singlet state and triplet state is explained by the simple formula. First I will explain the formula, later how these are singlet electrons are electrons are arranged in the singlet state and the triplet state. Okay. By using the multiplicity rule, multiplicity J, that J is equal to J of a molecule is equal to mod 2s plus 1, mod 2s plus 1, where s is equal to sum of spins of electrons. Right. When spin of electron is, you know that in the orbital one electron is there. It may be oriented in two ways. This is one way and this is another way. Sorry, reverse. This is another way. Right. Now, suppose this is oriented like this, it is assigned to plus off. It is oriented like this, it is assigned as minus off. Right. If the orbital is filled with two electrons, the two electrons are oriented like this in opposite spins. This is having plus off and this is having minus off. Suppose this is minus off and this is plus off. Right. Now S is equal to total sum of plus minus off. The minus off will be cancelled, 0. S is equal to 0. Now substitute this S value in the 2s plus 1, 2s mod 2s plus 1, that is 2 into 0 plus 1. Therefore, we will get the 1 value 1. This is known as singlet. The electronic configuration is known as singlet configuration, and that state is also known as singlet state. The state of the orbital is known as singlet state. The orbital state is known as orbital state is known as singlet state, and electrons state is known as singlet electrons, electronic state. Right. Now coming to the triplet state. For example, in a orbital, the electrons are having parallel spins like this, or parallel spins. Suppose these two are the plus halves, these two are the minus halves. Now for this orbital, S is equal to plus half plus plus half, that is equal to 1. Here S is equal to minus half plus minus half, total minus 1. Here the plus 1 and a minus 1. Now apply the 2s plus 1 mod 2s. 2 into 1 plus 1 is equal to 2 plus 1, that is equal to 3. Here minus 1. 2 into minus 1 mod plus 1. Minus 2, even then it is in the mod, that whatever the plus or minus is there in front of the digit, that will be cancelled. Therefore, that is taken as 2 plus 1, that is 3. In both the cases, 3 is coming. Therefore, that is known as triplet state. The state is known as triplet state. Triplet state. When triplet state is observed, electrons are filled in a orbital with parallel spins. Parallel spin. Parallel spins means opposite, that is oriented like this, plus half of spin, or minus half spins of the two electrons. That leads to the formation of triplet state. Now that energy, the orbital state or the electronic state is known as triplet state. Right. Now coming to the decaying of the activation state. Before going to the decaying of activation state, here the singlet states and triplet state energy levels of the different bonds. When we coming to Phi to Phi star and N to Phi star orbitals, we need to understand the energy states and singlet states and triplet states. Right. Now first coming to the sigma molecular orbitals. Sigma molecular orbitals are these are the ground state, or S0. S0 indicates the singlet zero energy or ground state. State of Phi molecular orbital. Phi molecular orbitals, that is BMO molecular orbital, anti-bonding molecular orbital. Here in the ground state, 2 electrons are filled in with the opposite spins. Because we said that this is the singlet state. S0 indicates the singlet state. Right. Now, if you provide the energy photochemically, not the thermally. Here we are discussing about the photochemistry. That's why I am applying the photochemical energy. We can get the two kinds of the transitions. Two kinds of the transitions. That is just okay. This is the non-bonded energy level. This is the bonding molecular orbital. This is the anti-bonding molecular orbital. Now in this case, this is another one. Non-bonding energy, bonding molecular orbital, and anti-bonding molecular orbital. Now these two electrons, the excited electron, whenever you are providing the electron energy, the electron is excited from the VMO to the AVMO. Now the excited electron is excited in two ways. One, it is carrying its spin, the same spin, or it is inverted its spin. Look at here. Suppose this electron is excited with the same spin, then the arrangement is, the electronic configuration is like this. Now, if it is excited with the reverting its spin or inverting its spin, okay, therefore the spin inversion takes place. Plus of 2 or minus of 2, plus of or plus of 2, minus of, vice versa. This takes place. Now this is known as triplet energy level, triplet state. This is known as triplet state. We simply call it as first triplet energy state. First triplet energy state. Now coming to the, this one is first excited singlet state. First excited. Here you need to include the excited word. Excited. First excited singlet state. Generally, the triplet state is shown with the first triplet state T1. Singlet state is shown with the S1. Right. Now, in most of the cases, this triplet state is not possible in the case of sigma electrons. In the case of sigma electrons, the triplet energy level is, most of the cases, it is not possible. Right. Here, why I am showing this is not possible? Here, selection rules are there. Based on only selection rules are two rules. One is, whenever the electron is excited from the molecular orbital, bonding molecular orbital to the anti-bonding molecular orbital, whenever we are providing the energy, that is excited with the same spin, that is allowed. If it is exciting the electron from the bonding molecular orbital to the anti-bonding molecular orbital, involving the inversion of spin, that is the forbidden. Right? That's why this is the forbidden transition. This is known as forbidden transition. This is known as allowed transition. This is known as allowed transition. This is known as forbidden transition. Look at here. That means always in the case of sigma star electron transitions, singlet state will be generated instead of triplet state. The triplet state involving the inversion of the spin state of the electron. That is forbidden. That is the reason singlet state is more commonly generated in the case of sigma to sigma star transitions. Right. Now, when you coming to the energy comparison, when you compare the singlet state and singlet excited state and triplet excited state, singlet excited state is having the higher energy than the triplet excited state. Even though it is having the highest energy, the allowed transition is first excited singlet state. Possibility is first excited singlet state, not the first excited triplet state. The energy comparison is ES1 is having more energy than the energy of the triplet state 1. This is about the sigma bond electron transitions, right? But even though it is the forbidden in the general case, for example, heavier atoms like bromine, chlorine, iodine, sulfur are present in the molecule, or even with O2 is also oxygen, peroxy bond is there, that this rule will be broken. That means the forbidden rule will be broken. Then triplet state will be generated. Triplet state is generated. It is the reason the excited state, the energy on excited state, singlet excited state is higher than the corresponding triplet state. Right.
సార్ సార్ ఇప్పుడు S1 ఎనర్జీ అయి ఉన్నప్పుడు మరి ఇక్కడ కింద రాశారు కదా సార్ లో అవుతుంది కదా సార్ అబ్బో ప్రిన్సిపల్ ప్రకారం.
Just listen here. Just listen here. In the general case, right, energy of S1 is less than the energy of T1. Okay, this statement I forgot to give you, right? Whenever the molecule is attached with the chlorine, these are the heavier atoms, bromine, iodine or sulfur, even with the peroxy bonds are there in the molecule, the forbidden rule will be neglected. That means the triplet state energy is generated. Why? Because here all this chlorine, bromine, iodine and sulfur are having a pair of multiple pairs of electrons, right? These electrons involving in the transitions that leads to the increasing the energy of S1 state and decreasing the energy of T1 state. That is the reason whenever it is undergoing the excitation, triplet state is the more available than the singlet state, right? Whenever these atoms are present in the molecule, the energy of the singlet state is increases, and a lower energy state of the triplet state is available. Due to that reason, that is generating the triplet state, not the singlet state. But in the
ఇప్పుడు ఎగ్జామ్ లో అడిగితే సార్, ఇప్పుడు ఎగ్జామ్ లో అడిగితే ఈ ఫస్ట్ కేస్ చెప్పి మళ్ళీ ఈ ఫస్ట్ డయాగ్రామ్ డ్రా చేసి మళ్ళీ సెకండ్ డయాగ్రామ్ కూడా డ్రా చేయాలి కదా సార్?
yes, ఫస్ట్ ఇది చెప్పాలి. ఫస్ట్ ఎగ్జామ్ లో ఈ ఫిగర్ డ్రా చేయాలి. డ్రా చేసి ఈ రెండు రూల్స్ చెప్పాలి.
allowed for
general case,
okay sir,
if the electron is excited with the same spin, that is allowed. If electron is excited with the inversion of spin, that is the transition is forbidden. In this case, in the allowed cases or in general cases, the transition involves the formation of singlet state is having the lower energy than the triplet state energy later. But this rule is broken when the molecule is associated with the chlorine, bromine, iodine, sulfur or oxygen. That energy states will be reverted. That is, the triplet state energy will be decreases. During the electronic transition state, the triplet state is more available than the singlet state. Therefore, the triplet state is more commonly generated. That is the point you need to mention.
Okay, sir. Okay, sir. Understood.
Right. This is about the sigma star transition. Next, coming to the Phi to Phi star transitions. In the most of the cases, next, coming to the Phi to Phi star transition. This is the non-bonding energy level. This is the pi molecular orbital and Phi star molecular orbital. And sometimes the molecule is associated with the carbonyl carbon. Suppose here the pi electrons are there, non-bonding electrons are there. In such case, non-bonding electrons are also available. In that case, N2 Phi star transitions are also possible. Okay. Now, here I am going to explain two types of transitions. That is the Phi to Phi star transitions and N2 Phi star transitions. Right. The first case, we are providing the energy. It undergoes the N2 Phi star transitions. N2 Phi star transitions. This transition required energy almost 270 nanometers of energy. Radiation is required. Then it leads to the two kinds of transitions. Two kinds of transitions. One is right. This is N to Phi star transition. That is, the electron is excited from this N electrons to N orbital to Phi star orbital. Therefore, one electron is remained here. One electron is remained. Here both electrons are there. The excited electron may undergo the spin inversion. Now it leads to the formation of triplet state spin inversion. That is triplet N2 Phi star transition. Into Phi star transition. This is also denoted as T1 state. T1 state. Here it is involving spin inversion. According to the rules, it is the forbidden transition. It is the forbidden transition. Now coming to the another kind of transition, N2 Phi star transition involving the spin reversion, retention, not spin reversion, spin retention. This is the non-bonding electrons, one Phi molecular orbital, Phi star molecular orbital, N. The electron is excited from the N molecular orbital, then electron is excited with the same spin. Electron is excited with the same spin. Or we can change this. Right. Opposite spins are there when we compare to the N orbital and the Phi star orbitals. Now this is known as N2 Phi star energy level or S1 state. S1 state. This is known as S1 state. This is the two cases. One is the N2 Phi star triplet state, that is the T1 state. N2 Phi star singlet state, that is the S1 state. S1 state. When we coming to the energy comparison, energy of singlet N2 Phi star is greater than energy of triplet N2 Phi star. Is the energy general condition. This one. Energy of singlet N2 Phi star is more than the energy of triplet N2 Phi star. But it is the forbidden thing. Why? It is undergoing this spin inversion. Due to that reason, this will not occur. This will not occur. Right. Next. Coming to the second type, Phi to Phi star. This will be takes place at nu. This takes place at 180 nanometers, lower higher energy transition state. That means the wavelength of the light is increases, energy will be decreases. Right? Wavelength of the light is increases, energy will be increases. So decreases. Wavelength of the light is decreases, higher energy is increases. Now this is the higher energy transition. Due to that reason, the electron is excited from the Phi to Phi star. Here also we see in two conditions. Phi N Phi star. Then the electrons will not disturb here in the Phi orbital, but the electrons are disturbed in phi, that is the electron is excited from the pi to phi star. Therefore, now the electron is reached here. This is one. Phi n phi star. Only one electron. Space. Right. So spin is inverted. Spin is inverted. Right. This is n orbital. Now look at here. The spin is inverted. This is the triplet state energy. Triplet
స్పిన్
state
సేమ్ ఉంది
transition.
కదా సార్?
Where
పైలో పై స్టార్ లో సేమ్ స్పిన్ ఉంది కదా సార్? స్పిన్ రిటెన్షన్ అయింది కదా సార్?
same spin.
దట్స్ వై స్పిన్ ఇస్ రిటైన్డ్.
Yeah, spin is not retained. Look at here. Actually, this electron is excited. What is the spin? This one.
ఓకే
Plus
ఓకే
half,
ఓకే,
suppose.
ఏదైతే
Now
రాసినామో
it is
అది కాకుండా
inverted.
రాయండి. ఓకే సార్,
Right.
అర్థమైంది సార్.
Spin is inverted. Friend, this is the triplet and pi to phi star transition, or it is denoted as T2 state of a molecule. T2 state, right? This becomes a T1 state. The T1 state means N to phi star transition, triplet state. The T2 state is pi to phi star triplet state, right? Here, this is the singlet state. That is singlet pi to phi star. Pi to phi star state. This is also denoted as S2 state. This is also denoted as S2 state. Now, how can you compare these electrons' energy? Look at here. Energy of singlet pi to phi star is greater than energy of n to phi star. Sorry, pi to phi star. Pi to phi star. This is the comparison of energy. Energy of the pi to phi star is more. Singlet phi star. Singlet energy pi to phi star transition is more than the triplet pi to phi star transition. Right? Now, coming to the Jablonski diagram. Deactivation of excited states. Deactivation of excited states. Excited. It can be explained based on Jablonski diagram. Jablonski diagram. If you look into this diagram, just a minute. Look at here. I think your molecule is always existing in, that is, state is called S0. S0 means ground state. This one is. This is known as ground state. Right. Then next energy level. This is the electronic energy level I am showing here. Electronic energy level. This is S1. S1, and the next energy level is S2, right? In between these are known as S1, S2, and S0, S1, S2. These are known as electronic excited level. Electronic excited levels. States, excited singlet, and first excited state, second excited state, right? In between the two electronic levels, we have vibrational levels. I will show you at a different case. This is the two electronic excited states. Suppose S0 and S1. In between, vibrational levels are there. These are known as, here the V0 started, and the V1, and so on, Vx levels. In between the vibrational levels, rotational levels are there. Each vibrational V1, V0 to V1, this is the R0, R1, R2, and Rx, like that. Similarly, here V0, R0, R1, R2, and Rx, like this. Every energy level, excited level in between the electronic excited levels, vibrational levels, and rotational levels are there. Suppose these are the vibrational levels. You take the two vibrational levels. These are the vibrational levels, V0 and V1. Rotational levels are there, R0, R1, R2, and so on, Rx. If you take the rotational levels, these are suppose rotational levels, R0 to R1. There is a translational energy levels. That means the four kinds of energy levels are there. One is the translational energy levels, rotational energy levels, vibrational energy levels, and electronic energy levels. Okay. In between the two electronic levels, several vibrational levels are there. In between the two vibrational levels, several rotational levels are there. In between the two rotational levels, several translation energy levels are there. Okay. These translational energies are easily changed whenever we are a small movement of the object. Even though every object having translational levels, rotational levels, vibrational levels, and electronic levels. This electronic level requires a higher energy when we compare to the vibrational levels. Vibrational levels are requiring the higher energy than comparing to the rotational levels. When you compare to the transition levels and rotational levels require the higher energy than the translational levels. This translation energy transitions will be takes place very easily whenever we create some movement of the molecule. Therefore, always the object energy levels will be exchanged between the vibrational levels and rotational levels and the translational levels at a simple energy conditions only. It will not require particular reaction, but particular energy level providing conditions, right? Okay, these are the electronic levels. These are not required here. That's why I'm removing this. Right. I think next class time is there already. Someone is waiting in the next link. Can I end up the session? Murali sir waiting in the Zoom room.
Okay, sir. Okay, sir. మళ్ళీ నెక్స్ట్ వీక్ ఇట్లా ఉంటుందా సార్? సండే ఉంటుందా సార్ క్లాస్?
Sunday, Saturday. I think Saturday is also.
Saturday, Sunday రెండు ఉంటుందా సార్ ఆన్లైన్ లో?
Yeah, dates are also given in your message. Please
yes
see
sir.
That. Right.
Yes sir.
Okay, thank you.
Thank you sir.
In the next class we will discuss.
చాలా ఇంట్రెస్టింగ్ అనిపించింది సార్ ఈ రోజు.
Right. Thank you.
Okay, thank you sir.
Thank you, sir.
జయశ్రీ అక్కో ఉన్నావా ఇంకా?
join at 2 o'clock again.
1:30 కదా నెక్స్ట్ క్లాస్.
But 1:30, but we need to eat lunch.
కానీ ఏం కంటిన్యూస్ గా క్లాసెస్ ఉన్నాయని సార్, ఇట్లా చేస్తే అంటే చెప్పి బతకాలా, ఏం చేయాలి?
మరి లంచ్ తినాలి కదా, అంతే తినేసి వద్దాం 2 o'clock.
ఏమంటాడు సార్ మరి?
సార్ పర్మిషన్ తీసుకుందాం 15 minutes.
లాగిన్ కావాలటైతే మరి
అయితే సార్ వచ్చాక తీసుకుందాం.